everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know that alcohols can be classified as primary, secondary or tertiary, and then we're going to understand the reactions of alcohols with oxygen and air, halogenating agents, so PCl5 to produce chloroalkanes, 50% concentrated sulfuric acid and potassium bromide to produce bromoalkanes, red phosphorus and iodine to produce iodoalkanes, and potassium dichromate in dilute sulfuric acid to oxidize primary alcohols to aldehydes, including a test for the aldehyde using Benedict's or Fading solution and carboxylic acids, and secondary alcohols to ketones, and also the concentrated phosphoric acid to form alkenes by elimination. We're then going to look at two core practicals. The first one will be the oxidation of ethanol, and the second will be the chlorination of 2-methyl-propantool using concentrated hydrochloric acid. Now I'm going to introduce alcohols. So alcohols are a homologous series with the general formula CnH2n+1OH. So the first alcohol we have is methanol. So that would be when you sub in n equals 1. So we would get a formula of CH2 multiplied by 1 plus 1 OH. So methanol has the formula CH3OH. Alcohols are produced industrially by hydration of alkenes in the presence of an acid catalyst, and they can be classed as primary, secondary or tertiary alcohols. So for primary alcohols, the carbon which is attached to the OH only is attached to one alkyl group. So we have the carbon and the OH, and we have the carbon is attached to another two hydrogens and only one alkyl group, which is what the R stands for. So this is a primary alcohol. The secondary alcohol is where the carbon which is attached to the OH is attached to two alkyl groups. So we have the carbon attached to the OH, and then we have one alkyl group and another alkyl group and a hydrogen. And so this is a secondary alcohol. And then for the tertiary alcohol, we have three alkyl groups attached to the carbon, which is attached to the OH. And so we have carbon and the OH, and now we have three of these alkyl groups. So this is a tertiary alcohol. Alcohols have a higher melting and boiling point compared to their corresponding alkane, and this is due to hydrogen bonding. And we get hydrogen bonding between hydrogen and a very, very electronegative atom. And so because we have OH bonds, hydrogen bonding is present. And this is opposed to the weaker van der Waals forces between the alkane molecules, which take less energy to overcome and so have lower melting and boiling points. The shorter alcohols are soluble in water, and this is because they can hydrogen bond with the water molecules. However, the longer alcohols are insoluble in water, and that is due to the longer hydrocarbon chain, which is insoluble. Now we're going to talk about the oxidation of alcohols. Alcohols can be oxidized in stages using acidified potassium dichromate or sodium dichromate, and primary alcohols are oxidized to aldehydes, which are then in turn oxidized to carboxylic acids. And secondary alcohols are oxidized to ketones. And tertiary alcohols are not easily oxidized, as it would involve breaking a carbon-carbon single bond, which takes a lot more energy than breaking a carbon-hydrogen bond. And this is also the reason why ketones are not oxidized any further. About the different types of alcohols, a primary alcohol is one where the carbon which is attached to the hydroxide, so the OH, is only attached to one alkyl group. A secondary alcohol is where the carbon attached to the OH group is attached to two alkyl groups, and a tertiary alcohol is where the carbon which is attached to the OH is attached to three alkyl groups. And so this is why you can't oxidize the tertiary alcohols, because the carbon-carbon single bonds that we have take a lot more energy to break than the carbon-hydrogen bonds. So the first example we're going to look at is ethanol, which is a primary alcohol, and it's oxidized ethanol, which in turn is oxidized to ethanoic acid. So we start off with ethanol, which looks like this. So CH3, CH2, and then OH. And then now we draw an arrow, and we use this symbol, so we use an O in square brackets to indicate that we're oxidizing. And so we label this oxidation. And the actual conditions we have it in is that the alcohol is in excess and there's no reflux. And we're going to be looking at reflux a little bit later. So we have an excess of alcohol and also no reflux. And then this will form the ethanol. So ethanol has this formula, so CH3, C, and then OH, like this. And so this is an aldehyde. So we started off with ethanol, and then now we've ended up with ethanol, which is the aldehyde. And then we can oxidize this even further using the square brackets O, and we label it oxidation. And this time we need the oxidizing agent in excess. And also we do have reflux this time. So this forms the ethanoic acid, which has a display formula of CH3, C, double bond O, OH. So this is our ethanoic acid. So the O with the square brackets indicates that we're oxidizing. However, we can also write arrows like this. So you can have an arrow and you'd write H plus because it's acidified potassium dichromate, and you would put down the potassium dichromate. And so this could be used instead of the O with the square brackets. Now for the second example, we have propantuol, which is a secondary alcohol, and we're going to oxidize this to propanone, which is a ketone, using acidified potassium dichromate. So what we have is we have propantuol, so CH3, then CH, and this time we have the OH on this carbon, and then a CH3, and then we're going to use this square bracket and the O again, and we're going to form the propanone, so CH3, C, double bond O, and then CH3. And we're also going to form water. So this is propanone, and this is propantuol. Now we're going to look at other reactions of alcohols that we need to know about. So the first is the combustion with oxygen, and we need to know that alcohols combust with a clean flame. So for an example of a combustion, we could have ethanol, and we react it with oxygen, and this forms 2 carbon dioxide molecules and 3 waters. And then the second reaction is a substitution with PCl5 to produce chloroalkanes. So what that would be if, again, we're using ethanol, we would have CH3, CH2, OH, and then react it with this PCl5, and then we would form chloroethane, and then POCl3 and hydrogen chloride. And this reaction with PCl5 can actually be used, and you would observe misty fumes because of the HCl gas. And then we need to know the substitution with 50% concentrated sulfuric acid and potassium bromide to produce bromoalkanes. So what we do here is we add potassium bromide and 50% sulfuric acid together, and this forms hydrogen bromide, and then we react it with the ethanol. So we have CH3, CH2OH, and then react it with hydrogen bromide, and this will form bromoethane and also water. And then with the next reaction, we're going to form a iodoalkane. So again, if we use ethanol, and we're going to react it with phosphorus iodide. So that's what we get when we mix red phosphorus and iodine together. So that has a formula of Pi3, and then this will form, we need 3 moles of this ethanol, and this will form 3 moles of iodoethane and also phosphorus acid, H3PO4. And so we can see that various halogenating compounds can be used to substitute the OH group for a halogen. And then the third reaction we're going to look at is the elimination with concentrated phosphoric acid to form alkenes. So we have, for example, we could use propan-1-ol. So propan-1-ol, which looks like this. Would then react with this concentrated phosphoric acid to form propene. And also a water, because we've removed the water by dehydrating. So the condition we would have to have for this reaction would be we have to do it in warm conditions and also under reflux. So reflux is when we have the condensation tube on top of the pear-shaped flask, and so when the vapors condense, the condensed liquid then drips back into the flask. And then we also have the role of the reagent as the dehydrating agent. So the phosphoric acid is a dehydrating agent. And some secondary and tertiary alcohols actually can give more than one product when the double bond forms between different carbon atoms. So for example, if we look at butan-2-ol, so we have 4 carbons in the main chain, and then we'll have an OH here on the second carbon. And then these are all hydrogens. And from butan-2-ol, we can actually have 2 products. So the first is but-1-ene. So if the double bond forms here, then we'll have but-1-ene. However, we can also have the double bond forming the other way. So we can remove the water like this, or we can remove it like this. And so the double bond could be formed in a different place as well. So this time we'd have 3 hydrogens, and then carbon with another 2 hydrogens, then a double bond, carbon, then a hydrogen, and then a CH3. So this would be but-2-ene. And then for the but-2-ene, we can actually get 2 different isomers depending on how we draw the molecule. And this is because of the lack of rotation around the double bond again. And so what we can get is, first we can draw it like this. So we have the carbon-carbon double bond, and then if we have a hydrogen and a methyl over here, and hydrogen, this would be the E-butene, because the two substituent groups, which aren't hydrogens, are on opposite sides to each other. Whereas if we drew it like this, and we had the methyls like this, then this would be the Z-butene. Because if we split up the double bond horizontally, the two substituent groups are on the same side, and so we call it Z-butene. Now we're going to look at a core practical, which is investigating the oxidation of ethanol. And I'm going to run through the quick method. So the first thing you do is carefully add 20 centimeters cubed of acidified sodium dichromate solution to a 50 milliliters pear-shaped flask and cool the flask in an ice water bath. The acidified sodium dichromate is the oxidizing agent. And so we set the flask up for reflux, keeping it in the ice water bath. And also one thing to note about the acidified sodium dichromate is that you should wear gloves when handling it because it can be corrosive. And then step 3 is to place a few anti-bumping granules into the pear-shaped flask. We place anti-bumping granules into the flask because it prevents the formation of big bubbles, which can cause an uneven heating of the liquid. And so that's why they're useful. And then for step 4, we measure out 1 centimeters cubed of ethanol, and then using a pipette, we add this ethanol a few drops at a time down the reflux condenser. And this must be done really slowly, and we allow for the reaction to subside after each addition before adding more. So we allow for the reaction to kind of do its thing before we add more ethanol. And when all of the ethanol has been added, we remove the ice water bath and allow to warm to room temperature. And then we position the flask in a hot water bath using water from a kettle and light a Bunsen burner and maintain a boiling water bath for 20 minutes. And then we allow the apparatus to cool. The last step will be to distill the product using the distillation apparatus, which is on the right, and collect 3 to 4 centimeters cubed of clear colourless liquid. And this colourless liquid that is collected should be a carboxylic acid. And so we can test this out by adding some sodium hydrogen carbonate, and it should form carbon dioxide. And then we can use some lime water to test for the carbon dioxide, because it should go cloudy in the presence of carbon dioxide. Now we're going to look at the second core practical, which is the chlorination of 2-methyl-propantuol with concentrated hydrochloric acid. So the method is that the first step, you add 35 centimeters cubed of concentrated hydrochloric acid and 10 centimeters cubed of the 2-methyl-propantuol, which is a tertiary alcohol, to a 250 centimeters cubed conical flask. You then put the rubber bung in and swirl the flask gently. You then open the bung to release the pressure from the fumes from time to time. So this is going to be from the HCl. And repeat this regularly for 20 minutes. We then use a spatula to add 2 to 3 scoops of anhydrous calcium chloride and shake. And at this point, there should be 2 distinct layers. And in this case, the upper layer will contain our desired product, whereas the lower layer will be the aqueous layer. We then transfer the contents of the flask to the separating funnel and allow the layers to separate and discard the lower layer. We then close the tap and keep the organic layer in the separatory funnel. We then add a solution of sodium hydrogen carbonate to remove the unreacted HCl and swirl gently. We stop at the separating funnel and shake it, and then invert the separatory funnel and open the tap to release the pressure due to carbon dioxide formed. We repeat this twice, and then remove the stopper and run off the aqueous layer. We then run the organic layer into a 50 centimeters cubed conical flask and add a spatula of anhydrous sodium sulfate, which acts as a drying agent. We then swirl the contents and leave the flask to stand, and then decant the liquid into a 50 centimeters cubed pear-shaped flask before distilling it to purify the product. So now we're going to look at some questions. For question 1, pentanal can be oxidized to a carboxylic acid. Write an equation for this reaction and use the square brackets O to represent the oxidizing agent. So what we need to do is we first write down pentanal, so CH3, CH2, 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 CHO. And then we add one of these square brackets O's and then we form a carboxylic acid. So we should form pentanoic acid from pentanal, because we're oxidizing it. CH2, 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 and then COOH. And then for B, name the carboxylic acid. So this would be pentanoic acid, because it has 5 carbons. And then for C, pentanal can be formed by the oxidation of an alcohol. Identify this alcohol and state the class to which this alcohol belongs. So we know that primary alcohols can be oxidized to pentanal and then to pentanoic acid, so an aldehyde and a carboxylic acid, whereas a secondary alcohol can only be oxidized to a ketone. And so this alcohol must be a primary alcohol. And the reason why secondary alcohols can only be oxidized to ketones is that with a ketone, for example, if we have pentanone, so we have 5 carbons, and then we have a double bond oxygen in the middle. And so these 3 bonds, so the carbon bonds and also the carbon and oxygen bonds, are really, really strong. So it takes a lot of energy to overcome. And so we can't oxidize them any further compared to the carbon hydrogen bonds that we usually are trying to break, which is a lot easier.